Let's just dive right into this. Welcome to The Explainer. Today, we're jumping straight into the fascinating and, honestly, kind of terrifying microscopic true crime chemistry of ruined wines. We're tracking down the invisible saboteurs that can take literally years of meticulous vineyard work and just destroy it from the inside out.
Imagine uncorking a beautiful, carefully aged vintage you've been saving for a special occasion. You pour it into the glass, but instead of that vibrant ruby or crystal clear gold you're expecting, it's murky, it's cloudy. It might even have this bizarre brownish tint, or worse, a harsh metallic bite. So what happened? How does a pristine wine suddenly turn into a swampy mess? Well, the answer lies in trace metals.
The sensory experience of a ruined bottle is, quite frankly, a tragedy for any wine lover. The crime scene usually looks like this: milky clouds, rancid aromas, and muddy brown tints. The wine completely loses all those fresh, fruity notes you actually want. Instead, you're hit with a harsh astringency, a bitter metallic flavor, and an appearance that makes it totally undrinkable. The stakes here are incredibly high for winemakers, which brings us to our main suspect.
The formal definition of this disaster in the enological world is casse. It's a physical-chemical instability. But simply put, it's the physical manifestation of microscopic sabotage. Trace metals sneak into the wine, react with other elements, and form solid compounds that literally precipitate out of the liquid. It completely alters the wine's appearance, its aroma, its flavor, and its texture.
But how much metal does it actually take to ruin an entire batch? Get this, just 10 milligrams per liter. That is the tiny, tiny threshold of iron needed to trigger an absolute disaster inside the bottle. Now, to be fair, all wines naturally have a little bit of iron, usually 2 to 5 milligrams per liter naturally drawn from the soil, but once it creeps over that 10 milligram mark, which often happens because of winery equipment, the wine is in grave danger.
Section 1. Ferric Casse, or iron oxidation.
This first primary culprit happens most often in red wines, mostly because grape skins naturally contain more iron, and this brilliantly illustrates the actual crime taking place. Iron and oxygen act as partners in crime. When the iron in the wine, that's the Fe+2, is exposed to oxygen, it oxidizes and transforms into Fe+3. And this oxidized iron is aggressive. It's looking for something to bond with, and when it finds it, it creates those undesirable wine-ruining compounds that physically drop right out of the liquid.
So the real kicker is what that oxidized iron actually decides to bond with, because it has a few favorite targets. If it bonds with biphosphates, like the ammonium phosphate winemakers use as a fermentation nutrient, it creates white Casse. This forms insoluble white salts, mostly in white wines. If it attacks the tannins in red wine, it creates blue Casse, resulting in this really strange bluish ferric tannate. And if it goes after the anthocyanins, which are the pigments in red wine, it forms black Casse, creating a dark, murky, totally insoluble complex.
But here's the thing. Iron rarely acts alone. Iron oxidation is encouraged by a very specific set of conditions. High pH levels, anything above 3.4, make iron more soluble. Low storage temperatures actually increase the insolubilization of those awful ferric phosphates. Prolonged oxygen exposure and high polyphenols, they speed things up too. But the absolute worst accomplice? Copper. Copper acts as an extremely eager catalyst. It oxidizes way more easily than iron does, and when it's present, it aggressively pushes the iron to oxidize even faster. It's basically a chemical gang-up.
Which brings us to part 2. Cupric Casse, the copper cloud.
Unlike iron, copper usually sneaks into the winery straight from the vineyard, almost always via fungicide treatments used to fight mildew. And hey, if you thought iron was sensitive, get a load of this. 0.5 milligrams per liter. It takes a ridiculously minuscule threshold of copper residue to put a wine at risk of cupric Casse. Now, a lot of copper is naturally filtered out during fermentation because it binds to the yeast, but if even half a milligram remains, the wine is essentially a ticking time bomb. Let's compare the MO of these two villains side by side, because they operate in completely opposite ways. Ferric Casse is driven by oxidation, meaning it absolutely needs oxygen to thrive, and it predominantly targets red wines. Cupric Casse, on the flip side, is driven by reduction, which is the exact opposite of oxidation, and it almost exclusively attacks white wines.
So here's the specific mechanism for our copper saboteur. In white wines, over a prolonged period of bottle storage, and especially when exposed to sunlight, the copper reduces from Cu+2 to Cu+. In this reduced state, it creates cuprous sulfide, which aggressively binds to the proteins just floating around in the white wine.
This creates a milky, whitish precipitate. The wine turns a muddy orange or brown, totally loses its fresh fruit aromas, and takes on a really harsh metallic taste. Red wines usually escape this fate just because their proteins are already bound up by tannins, which leaves the copper with absolutely nothing to attack.
Part 3. The investigation. Detecting the saboteurs.
So how do winemakers actually catch these invisible saboteurs before they ruin an entire batch? Well, to uncover hidden iron instability, they run a forced oxidation test. It's incredibly straightforward, but highly effective. Step 1, they fill a clear glass bottle halfway with the wine. Step 2, they shake it vigorously to absolutely saturate the liquid with oxygen. And step 3, they incubate it at cellar temperature for 7 days. If the iron levels are dangerously high, a precipitate is going to form right at the bottom of the glass. They've effectively forced the ferric case to show itself in the lab before it happens in the bottle.
Testing for copper, though, requires a totally different trap. Because Casse is driven by reduction and light, oenologists will take a bottle and expose it to direct sunlight for 7 days. Alternatively, they can stick it in a dark incubator at a warm 30 degrees Celsius for 3 to 4 weeks. They are looking for dark red or brown precipitates. If those show up, they know for sure they've got a copper problem on their hands.
Part 4. Other dangerous metal contaminants.
While iron and copper are definitely the most common saboteurs, there are other, honestly even more dangerous heavy metal accomplices that can infiltrate the winery. And these aren't just a threat to the wine, they're a threat to us. Let's look at this rogues gallery. Arsenic, cadmium, and mercury can occasionally sneak in from old vineyard treatments used for wood diseases. Then there's lead, which usually leaches from ancient, poorly maintained winery facilities and old pipes. The international limit for lead is strictly capped at 0.15 milligrams per liter. We've also got aluminum, which comes from modern equipment and has been linked to serious health risks. And finally, zinc. Now, zinc is actually wonderful for our immune systems in trace amounts, but if it gets into the fermentation tank, it aggressively damages the yeast and gives the wine an absolutely awful metallic taste. So good for you, terrible for the vintage.
Part 5. The winemaker's defense toolkit.
Once these metals are detected, how does the winemaker actually fight back? Well, this brings us to the single most dramatic treatment in the entire winemaking process: blue fining. When metal levels are critically high, winemakers can use potassium ferrocyanide. This chemical binds incredibly tightly to both iron and copper, forming these heavy, insoluble complexes that just drop right to the bottom of the tank, which allows the clean wine to be filtered right off the top. It is incredibly effective, but there is a massive catch.
And I mean a massive catch. If the ferrocyanide is added in excess and does not combine with the iron, highly toxic and lethal hydrocyanic acid is released. Yes, you heard that correctly, lethal. If the winemaker miscalculates the dosage and adds even a tiny bit too much ferrocyanide, it literally creates a deadly poison. Winemaking isn't just about tasting grapes, right? It is a highly precise and potentially dangerous laboratory science. Every single blue fining treatment requires rigorous prior lab testing with different doses, just to ensure absolute mathematical precision.
Because of those genuinely terrifying stakes, winemakers have a whole arsenal of alternative, much safer weapons to prevent metals from ruining the wine. Ascorbic acid, which is really just vitamin C, is a fantastic antioxidant that stops iron from oxidizing in the first place. Gum arabic acts as a physical shield. It's a protective colloid that literally gets between the molecules and stops them from binding together. Bentonite clay can be used to dramatically drag proteins out of the wine, so the copper has absolutely nothing to bind to. They can even heat the wine to 75 degrees Celsius for 15 minutes to destroy those proteins entirely. And for iron, they can add calcium phytite, which safely forms complexes with the iron to just drop it right out of the wine.
Which leaves us right here. Next time you uncork a pristine, crystal clear bottle of wine, will you just taste the fruit? Or will you taste the meticulous, high-stakes chemistry that saved it from microscopic sabotage? Every flawless glass is quite literally a triumph of science over nature's little chemical saboteurs. Thanks for joining me on this explainer, and keep learning.